put this up there. I am going to get all right. So there are two different ways that we need to know how to search. There are obviously many, many, many different ways. Yeah, I know to actually search, but we are only going to learn about two of them. So the two that we are going to learn about are called linear and binary search. So I'm actually going to go through this. I will post a link in the chat so you can play along if you'd like, but I'm actually going to go through it. Oh, what happened? Right. So here are the there we go. All right, so these boxes, the contents of the boxes are in a random order. So, oh, let me post it in the chat quick. So if they're in random order, what should I do? If I don't know what's in the boxes, I don't know what order they're in. I have 6 guesses to find the number 429. Start what? Okay, which one should I pick? But like, what would you do if you were looking for it? You probably start at 1. You start at one end, right? Oh, well, and you'd be right. Let's try that again. Right, 252. All right, 324, that's not it. So we move to the next one. Still not it. There's no advantage to picking any of the other boxes, right? We're just, we don't know what order they're in, so we're just kind of randomly going through, and eventually we get to it, right? Like if you were looking through a deck of cards and you were trying to find the king of spades and they were all shuffled, right? You wouldn't just start picking out random cards. You just start at one end and you would, you know, go through them one at a time until you found the card you're looking for. So again, random order, we don't really have a choice here, right? Like, yeah, we could pick random ones, but just for ease of use, right, and remembering which ones we've seen before, we might as well just start at one end. Oh, I found it already. Might as well just start at one end and go in order until we find it. There's no advantage to doing anything else. This time, there's a little bit of a wrinkle. I have 9 boxes, and I know that they are in order. So I have a deck of cards, they're in order, and I've picked out 9 cards and kept them in order. In this case, I think the numbers go from like, I don't know, 0 to 100, 0 to 1,000, I'm not really sure. But they're random, right? We don't know if the contents of the boxes are 1, 2, 3, 4, 5, 901, 902, 903, or if it's like 10, 50, 234, 235, 998. Like, we don't know what's in the boxes. All we know is that they are definitely in order from smallest to largest. So which one should I pick first? Yeah, Peter.
The middle.
Why the middle?
Well, because like then you can like adjust your next guess based on whether it's higher or lower than both.
Right. So what Peter's saying is if I pick the middle one here, it's either going to be higher or lower or exactly my number. In this case, it's higher. And if all the box's contents are still in sorted order, what do we know about all the boxes to the right of that one? If they're in sorted order, what do we know about them compared to 209? They're bigger. So is 34 going to be to the right of that middle box? Definitely not, right? We know that it's sorted, so we know everything to the right is 209, so we can get rid of half of our boxes with one guess. So what should I guess next? Two thoughts on this. Box 1, 2, 3, or 4? Yeah, good. 3? 138. So which box can I get rid of? Box 4, right? I could have picked box 2. Doesn't really matter. It's still going to work out the same. So now I have to just pick box 1 or box 2. I'll pick box 1, and there it is. So it took me 3 guesses instead of, you know, however many going from one end to the other. So now I have 25 boxes. So again, if I start at one end and go all the way to the other, it might take me 25 guesses. But if I pick the one in the middle, say 13, what can I do to all the boxes from 14 to 25 now? Cut them out, right? I know that box 13 is 308, so I can cut out all the boxes to the right because mine is less than that. So half of 13 is 6.5. So I could pick 6 or 7. It doesn't really matter. 203. So now that one is too small, so I can get rid of all the boxes to the left. I go back. I pick the middle one. 1, 2, 3, 4, 5. So I actually have a middle one this time. Go. So I can keep getting rid of half of them every time, which is pretty nice. All right. So this is the, all right, so let's watch a video. Gonna work? It's gonna work. Let me mute myself so you don't get that feedback.
Say you have a large amount of information in an array or list, and you're looking for one value in particular. In order to find that one value, you need to search through the array or list for that value. There are a few ways to do this, the first and simplest of which is called a sequential search. A sequential search is exactly what it sounds like. You typically start with the first item in the array or list and move progressively through it, one item at a time, until you find what you're looking for. While effective, this method can be inefficient, especially if the item you're looking for is towards the end, or not even present. The most efficient searching method we have is called a binary search, but it can only be used on data that is already in order. In a binary search, we actually start in the middle of the array, and then keep narrowing the search depending on whether the value we're searching for is larger or smaller than the one we're currently at. This is a vastly more efficient method because it allows us to eliminate half of the remaining values each time we access a value. Thanks for watching.
So Ben asked a really interesting question. He said, if you have a large number of items, is it faster to sequentially search, or is it better to try and sort them first and then use binary search? So I'm not going to fully answer this question right away because we'll answer it after we go through the search section. Sorry, the sorting section. But here's the question, right? Which is faster, a marker that doesn't work or a marker that does work? Which
Can't see that.
you see now? Oh, you just want to.
It was just too low before.
So which is faster? So linear search, sort, plus binary search. So this is a really interesting question. And we're just going to answer the first part first, and then we're going to answer the second part. So how long, say I have n objects, right? That's a typical way to say it. How long, or let me be more concrete. Let's say I have 100 objects, 100 numbers, and they're randomly assigned. On average, if I have 100 objects, how long will it take me to find a specific number if I start at the beginning and go to the end? What's the worst case scenario?
It checks everything.
All the way at the end. It has to check everything, right? So how many steps does that take? How many times does it have to check if I have 100 objects? 100 times. What's the best case scenario?
Only gets it on the first try.
Gets it on the first try. What do you think if I do this 1 billion times? All of those different numbers of checks will average out to about 50%. Right? Sometimes it'll go higher, sometimes it'll go lower, but generally speaking, right, if I did this 1 billion times, right, then 10 million times it would be in the first one, 10 million times it'd be in the second one, 10 million times it. Like not exactly those numbers, but pretty close. So on average, it's gonna take about 50 checks. If I have 100 numbers, what if I have 1,000 numbers? How many checks on average? 500. If I have 1,000,000 numbers, on average it has to check 500,000. If I have n numbers, on average, it has to check. Was that? Half of n, right. N over 2. So that's not bad. Right? It's not terrible. Now, binary search is a little trickier to figure out the math. Right? Let's say we have 8 numbers. So if I have 8 numbers, with one guess, how many can I eliminate? 4. With 2 guesses, I can eliminate 1 more. And with 3 guesses, I can eliminate 1 more. So worst case, 3. Oh, I should say average, then over 2, worst is n.
Wouldn't it be worst case score for the 8 one? The 3 eliminates it and it's the last one.
Right. So for binary search, best case is also 1. Worst case is 3. But let's make it a little bigger. So 16. How many can I eliminate with my first guess? 8, and then 4, and then 2, and then 1. 4 guesses. 32. How many do you think? 5 guesses. 64. Are you noticing any kind of trend here? Yes. Exactly. Right? Those are just the exponents because we're just multiplying by 2. We're dividing by 2 every time. So the number of guesses goes up by a factor of 2 every time. And so anything like 128, right, would be 7 guesses, but so would 100. Anything more than 64 might take 7 guesses. But as long as you don't have more than 128, you can just keep dividing by 2 and get down to 1. So does anybody know how to get from 128 to 7 using power of 2? What is that called? Anybody remember? Yes. Logarithm. So the log base 2 of 128 equals 7. You don't need to know this for any exam. I'm just trying to answer Ben's question, which is a really cool, really interesting computer science question. So, okay, let me put it this way. You need to know which is faster, linear or binary search, and why, but you don't need to be able to do the math to prove it. Let me put it that way. Okay, so you do need to understand just in terms of when would you use one or the other and why is binary search faster, but you do not need to prove it with math. So this is log base 2 of n is the worst case for that. All right, and we will come back because we need to know whether, n, obviously log base 2 of n is faster than n, but we need to know how fast we can sort to see if that plus that is less than that. So interesting question we will answer shortly. All right, so getting back to right. So we have two kinds of searches, sequential or linear, and then we have binary. And the key point to take away, and you will get questions on this, is it's literally the only thing you can do if your list is not sorted. There's no faster way than linear, right? If you do like random selections, that's still basically linear. So if you don't have any idea what your data looks like, if somebody threw a bunch of Uno cards in the air or whatever, and you're looking for something, there's no faster way than just looking through them one at a time. That is something you should remember. So here is a very common bug. What is the problem with this code? I see this all the time. Yes. It does not check all of the elements. What does it actually do? Checks the first one and stops? Right. Yeah, whatever J is, it just checks that one. And if that's the right one, it returns it. Great. If it's the wrong one, it says I didn't find it, but it doesn't check anything else. So I see this a lot. You don't want to return a -1, which means I didn't find it, until you've gone through the entire list. It gives up. Yeah, it gives up really easily. Here is a question for you. Kind of a trick question, but not really. What will cause the longest execution of a program if it's using a sequential search going through an array of integers? Which one of these? Type your answer in the chat. Not yet, not yet. Wait until I say go. So here, I'll make a poll. How about that? All right, so you can vote now in the poll. Which will cause the longest execution of a sequential search? The longest. So here's our votes. 9 votes for D, 1 vote for C. So most people think it's, why is it D and not C? Peter.
Because oftentimes it'll have to say, I'm so bad with words. It has to like do an extra, I think it has to do just an extra thing to check whether or not to return the last value, and then it moves on to say, I'm just going to return the top value.
Whoa, what just happened? No, went back. Sorry. There we go. So, right. So it still has to do all the checking. And if you are checking something complicated, then doing that check and not returning it, and then going on to do whatever happens when you have not found it is slightly longer than doing whatever you would do for C. So D is definitely the right answer. All right, not a trick question. I think everybody knows the answer to this one, so I'm just gonna say it's the first one. I don't think that's an interesting question, so. All right, so here's binary search that we talked about briefly. You keep going to the middle, and it doesn't really matter if you have an even number of things, whether you go middle -1 or middle +1. The math works out the same either way. So it's nice if it has an exact middle, but it doesn't really matter if it does or it doesn't. You can try it out if you want. But the key point here is that it only works if you have if you know that your data is sorted. So let's see if we can do this. So, oh, I see. So we're searching for the number 8. So it picks the middle, says that's too high, so it gets rid of the top half. It picks 5, it's too low, gets rid of the bottom half. Picks 7, too low, get rid of the bottom half. So let's find, I don't know, 20. Oh. So get rid of the bottom half, get rid of the bottom half, get rid of the bottom half, get rid of the bottom half. There you go. So it commonly uses integer division. And all that means is that if you have an even number, it'll take the lower one. So if you have like 1 through 8 and you guess too low, then the next one it's going to pick is 4, not 5, as the middle value. Oh yeah, and so that's a good point. So the last one is if, can't highlight, if it gets to a point where either, you're dividing by 2 and actually, let me just show this. I'll show this. Just to show the algorithm. So let's say I have 8 items. So n equals 8. So my left and my right and right. So right now my left is 0 and my right is 7. Because 0, 1, 2, 3, 4, 5, 6, 7. So I take 7. Oh, I guess I need to do it the other way. 1 to 8 for this algorithm to work. Whatever. 1 to 8 doesn't matter. Same thing. Oh no, because I subtract them. Whatever. Doesn't matter. 0 through 7. Let's be correct with our array nomenclature. So 7 minus 0 divided by 2. gives us 3, right? Because it's 3.5, but we're doing integer math. So 0, 1, 2, 3. So it's going to be this one. And say we're looking for the number 1, right? So it says if the target value is less than the value at the middle, so we're looking for the number 1 as our target. It is less than 4. So we set right equal to the middle value minus 1. So it was at position 3. So we're going to move this guy, right, because that wasn't it, to position 2. So our right is now 2, and our left stays the same. So now we have 2 minus 0 over 2 equals 1. So this is our new middle. And if the target value is less than the value at middle, which it is, our target value is 1, then we set the right down by 1. And then we have 1 minus 0 over 2 is 0, and we find our number. So basically all it's doing is dividing by 2. If it's too high, move it over 1 and do the same thing. If it's too low, move it up and do the same thing. That's all that pseudocode is doing. So if it gets to a point where the left and right are right next to each other, and so you add 1, and now they're trying to look at the same number, then you know that the target you're looking for is not in the array. Again, you don't need to memorize how it works. I'm just explaining it for your benefit. All you need to know how it works. You're not going to need to program it. Let me put it that way. So you need to understand how binary search cuts things in half, but you're not going to need to actually write a program that does it. Right. All right, so I am, well, let's see. I think you guys can get that. Let's not watch this. All right, so here is the runtime and worst case that I was talking about. And what we usually measure is worst case behavior. Yes. Oh, thank you. Yep. Yep. So usually what we compare is worst case behavior. So we haven't talked about sorting yet, but we will shortly. But you can imagine that if you have something that runs with n, that's pretty good, right? Because as you add more things to it, you can kind of predict that it's going to go up in a linear way, in a straight line. If it goes up with n squared, right? So you have to check everything for every time, then that's going to start going up as you add more items, right? The runtime is going to go higher and higher and higher pretty quickly. If you have 2 items, right, it has to check 4 times. If you have 100 items, it has to check 10,000 times. And so on, right? Like if you have like n cubed or n to the 4th, or even worse, if you have something like 2 to the n, every time you add more items, it's going to go way, way, way up. So what you want to do is try and lower that curve as much as you can. And binary search, log base 2, is very, very flat. It's even better than just going up with linearly with the number of items. So binary search is a very fast algorithm. So here's a comparison, right? Linear search, if you have 8 items, worst case you have to check 8 items. Binary, worst case you have to check 4. So it's actually worse for 4 items. Binary search is actually worse. All right, but it gets better quickly. So let me see if this is worth.
Today we're going to learn about Big O notation. So what is it? Big O notation is simplified analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, and we need a way to compare them and some idea of how long they'll take to run. Big O gives us an algorithm's complexity in terms of the input size, n. It gives us a way to abstract the efficiency of our algorithms, or code, from the machines they run on. We don't care about the stats of the machine, rather we examine the basic computer steps of the code. We can use Big O to analyze both time and space. There are a couple ways to look at an algorithm's efficiency. We can examine worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Let's talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that has a running time of 5n, we say that it runs on the order of Big O of n. This is because as n gets large, the 5 no longer matters. In the same way, as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page. We ignore or drop low-order terms when they're dominated by high-order ones. Take a minute and study this chart. It can be found on bigocheatsheet.com, along with a handy guide on the Big O of various important algorithms. Let's run a few examples so you can see what I mean by basic computer steps. We'll start with constant time. Imagine we have the following line of code. This basic computer statement computes x, and notice, it does not depend on the input size in any way.
So a better example of this is, say I have a deck of cards, right? And I tell you, or you can see, that there's only 3 cards in the deck. And I say, pick a card, any card. How long does it take you to do that? How many checks do you have? 1. Now I have a deck of cards with 1,000,000 cards. I have very large hands. And I say, pick a card, any card. How long does it take you to pick a card? 1, right? So that's what constant time means, is it doesn't matter how big your input is. It's always going to be the same amount of checks. So if I said pick 10 cards, right, it would take 10 checks, no matter how big my deck is. So it doesn't matter what that value is. If somebody says constant time, all it means is it doesn't change. It doesn't vary at all with the number of inputs.
We say this is Big O of 1, constant time.
The wrong one.
Their constant time. How do we compute Big O for this block of code? We simply add each of their times, and we get 3 multiplied by Big O of 1. But remember, we drop constants, so it's still Big O of 1. Let's look at linear time. Suppose we have the following for loop that prints the numbers 0 to n. We know the print statement is big O of 1. This means the block of code is n times big O of 1. In other words, big O of n. Here's another sequence. The first line we know, again, is big O of 1, and the for loop is big O of n. The total time is the summation of these two, but remember we drop low order terms. When n gets large, the time it takes to compute y is meaningless, as the for loop dominates the runtime. Finally, let's look at quadratic time. I think you can see that the print statement will be executed n times n, which gives us big O of n squared. Let's do two more examples covering everything we've talked about. Say we have the following block of code. What is its total runtime? Well, we know the runtime for each of these, so the total runtime is simply the max of the three. The nested for loop dominates here, so we get big O of n squared. How about this if-else statement? Pretend the sequence of statements in each clause have already been deduced to the big O's shown. We talked earlier that when we're discussing big O, we usually look at worst case scenario. So for this situation, we choose the largest runtime, which happens to be big O of n squared. I hope this gives you an understanding of big O notation. Let's wrap up by talking about the real world. When you're coding your algorithm, please realize that constants absolutely do matter. A lot of situations have small input sizes, so a constant of 2 or 3 could have a large impact. Lastly, for the same reason, be cognizant of best and average case. Depending on your application, this may be more applicable for your algorithm. As always, thank you for watching.
All right, so I'm going to actually move on to sorting, because we have like 15 minutes left. So there's only 2 sorts that we are going to look at for this class. There are many, 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 many different kinds of sorting algorithms, and there's an entire field of computer science. Is it this one? This. Here we go. So insertion, selection, bubble, shell, merge, heap, quick 3. So here's a whole bunch of different ones. The top row is all randomly organized. The second one is almost organized. The third one is backwards. And the last one is just like 5 different possibilities, and they're all duplicated. So it's kind of a fun then you can check out if you're interested. All right. Let me close that. Sorry. All right, so I'm actually going to go through this a little bit more quickly. If you were sorting a deck of cards, you would use something very much like selection sort. You would probably go through your deck of cards looking for the smallest one first and put that in the first position. So unfortunately, the way computers work is it is much more efficient Hey, it's the one right on the side, on the corner there. Yep, right there. So if I had a deck of cards, for example, and the ace, what's the first? Is it the lowest is clubs, right? Yeah, alphabetical. Clubs, diamonds, hearts, spades. So my ace of clubs is over here. So usually what you do is you look through it and you take that ace of clubs and you put it at the beginning. The difference between what you do with your hands and what computers do is if I did that, right, I would have to create a whole new array and put all the cards in that whole new array. So instead, what I do is I start with this card right here and I look at that card and I say, is it the ace of clubs? That's position 0. It's not the ace of clubs. Is this one? 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 Oh, look, there's the ace of clubs. I'm going to switch it. So say this was the 9 of hearts. I switched them to make this the ace of clubs and this the 9 of hearts. I don't really care where I put this one. I know I'm going to get to it later. So instead of creating a whole new array, it's much easier for me to just switch those two cards. So a deck of cards is not a perfect analogy as computer science, but this is how it works in reality. So then once I know the ace of clubs is there, do I ever have to check that again, that position? No, right? I never have to check it again. So I'm going to go now to position 1. And I can start looking for the next lowest card. Right? And I got to go, in reality, I have to go all the way through it because I don't know if there's a lower number in advance, right? If I'm searching for strings or if I'm searching for positive and negative integers, right? With a deck of cards, you already know what the lowest card is. But when you're actually searching for stuff, when you don't know what the lowest card is, you have to go all the way to the end and figure out which is the lowest one and then pop it back in there and then move on to the next one. Look for the lowest card, pop it back, so on and so on and so on. So that's called selection sort because you are selecting the next card and putting it in its proper place.
Today we're going to learn.
No, we're not. So the steps for the algorithm are Start at 0, right? Traverse to the end of the array, find the smallest element in the remaining array, swap it. Go to the next element, do the same thing. Go to the next element, do the same thing. Go to the next element, do the same thing, until you get to the second last item, because once you've gotten to the second last item, you know that the last one is already in the right position. So it saves you one step. Not a lot, but hey, we'll take it, right? So I'm going to post these slides so you can actually see how it works in Java. But again, I'm not concerned with you writing a selection sort code. All I care is that you know how it works. All right, so insertion sort is slightly different. It starts at the first index and finds the proper location for that card or that number in what you've already sorted. So basically, you look at each card. You're given a shuffled card, deck of cards, and you say, all right, well, the first card is the first card. It is what it is. The second card, is that bigger or smaller than the first card? If it's bigger, I put it behind. If it's smaller, I put it in front. Then I look at the third card and I say, where does it go? Does it go first? Does it go between those cards? Does it go at the end of those cards? Then I look at the fourth card. Where does it go with the ones I've already sorted? Fifth card, where does it go with the ones I've already sorted? So I start with one card and I just keep adding more and more in the deck in the proper order until I get to the end of the deck and I know I'm done. So instead of selecting the right card for the position I'm on, I insert the current card where it's supposed to go based on what I've already done. So you start with one card, there's no sorting there. The second card either goes before or after. The third card goes at the beginning, the middle, or the end, and so on and so on and so on. So you have to search through the stuff you've already done to find the right place for your next card. So that's the slow down part of that card. So I might actually play this.
Today we're going to learn insertion sort. Let's dive right in. We're given this array and we want it sorted in increasing order. Here's what we're going to do. We'll start at the left and work our way to the right, examining each item and comparing it to the items on its left. We'll then insert it in the correct position in the array. You'll notice that part of our array will be sorted as we progress. We'll mark those items with a green background. Let's begin and you'll see what I mean. We start at 2. Of course, there are no items to the left of 2, so we mark it as sorted. Moving on to 8, we compare it to 2 and leave it where it is. Our first 2 items are now sorted. Next, we have 5, which we can see is out of place. We know it needs to be after 2, so we swap it with 8. Our first 3 items are now sorted. On to 3. Again, it's out of place. We swap it with 8 and 5 until it's in the correct position. We're at our 5th item, 9, and I'm sure you can see that it's in the correct spot. Let's move to 4 and insert it in the correct place in the array. And that's it, we're done. Insertion sort is one of the most straightforward sorting algorithms. For your reference, here's the pseudocode. Insertion sort has the worst case time complexity of big O of n squared, where n is the size of the array. For example, today we're going to learn
So just like with a deck of cards, you would have your sorted stuff in your left hand. You look at the next card, and you kind of work your way backwards until you find the place it's supposed to be. And you stick it in there. It's exactly the same as a deck of cards in this case. All right, so where's mine? All right, so I've gone over that enough times. Like I said, I'll post these for you. So if the data is already in sorted order, there's nothing for insertion sort to do, right? If you have 1 through 9 and you're looking at 10, it doesn't swap because 10 is bigger than 9. In the worst case, right, it's reverse sorted and it has to swap every one all the way. That would be n squared, right? All right, so this is the information you need to know. Going through the exercises will help. I will also review some of this. But like I said, you need to understand how they work, not memorize the code or write the code. So merge sort, haven't had time to go through, but I guess I'll do that and post a video about it. Basically, in a nutshell, merge sort is split your deck in half, split it in half again, split it in half again, split it in half again until you only have 1 card in each hand. You put those 2 cards in order. You take your 2 cards from your left side, your 2 cards from the right side, put those in order. Put those in order, put those in order until you have 26 cards in each hand, and you're just doing which one goes first, left or right, left or right, left or right, and you end up with the whole thing in order. All right, I think that's all we have time for today. Yeah. Any questions on sorting or anything like that? Right off the bat.